I'd like you to list all the factors of 432. Okay, I'm kidding. I'm going to show you how. So it's hard to do with a big number like that, but with smaller numbers, like for example 12, it's super easy to say, well, let's see. 1 divides 12 because 1 divides everything. 2 divides 12. 3 divides 12. 4, 6, and 12. And you're done. But when you get to a number, when you're dealing with a number like 432, what could all the factors possibly be? So I'm going to show you an algorithm to work with, and then we'll do it with 432. I'm going to start with a small number, 24. 24 is a nice number because it has a lot of factors even though it's small. And we're going to find all the factors. And we should be careful here to know that when I say find all the factors, I mean all the integer factors. By using a process that finds all the factor pairs. I'm not going to write it, but I also mean integer factor pairs. All right. So start by creating a left and right hand column, and the first left hand entry should be the first integer, 1, and ask yourself, what would I have to multiply 1 by to get 24? Then inch up, does 24 divide by 2? Well, it's an even number, so of course it does. Then the next integer is 3. Now in this case we know that 24 divides by 3, but what if we didn't or couldn't tell? A shortcut to discover that would be to add the integers of the number, so 2 plus 4 equals 6. If 6 is divisible by 3, then 24 is also divisible by 3. So 3 times 8, the next largest integer, 4, times 6, the next largest integer, 5, does not. Then 6, well, notice that 6 is already written down, which means that this factor pair was already represented once. 7 does not divide 24. 8 does, so 8 times 3, but this is the same as 6. You've got just the same factor pair, only in reverse. 9 does not divide 24. 10, 11, 12 divides 24, but again, that was a pair that we already had written. And then 13, 14, 15, all the way up to 24 times 1, and that again is the first one. So look what happened here. Once I reached the place where I had a left-hand entry that was already on the right-hand side, nothing new happened. Either the number was not a factor, as in these cases, or the number was a factor, but I just got the same pair back that I had already produced above. So this is a really nice tool because it saves you all of this work. You only have to do half the work, and don't we like only doing half the work to get to the same place? So as soon as your next value is already on the left-hand side, you know you're done. So in this case, all the factors, these are all the factor pairs, there are 4 of them, but all the factors of 24 would be 1, 2, 3, 4, just writing down the left-hand side, and then up the right-hand side. 6, 8, 12, and 24. And that was super easy to do with 24. Let's see how much, if it helps us at all, with 432. And I'm kind of hoping it does because I sort of promised it would. So 432 is the same as 1 times 432. That's my first pair. 2, and I know it divides by 2 because it's even. So 400 divides by 2, leaving 200, and 32 divides by 2, leaving 16. 3, well, 4 plus 3 plus 2, so that's 7, 8, 9. 9 divides by 3, so I know that 432 divides by 3. So 3 goes into 4 1 time, leaving a remainder of 1. 3 goes into 13 4 times, leaving a remainder of 1, and 3 goes into 12 4 times. So that's 144. Now, the next integer is 4, and I can test to see, without having to look at whether 4 divides 132, I can actually look at my list. To get 4, I would have to double 2. So if I can half this number, then I know I have a factor pair. So I double 2 to get 4, and then I 216, that's 108. I take half of that one, half of the right-hand side. Now, if I could double 4, but I was unable to half the other side, meaning it was an odd number, then I wouldn't be able to do anything with it. So the next integer would be 7, and sometimes you just have to do long division. There are little tricks you can use, but sometimes it's just faster to do the division. So 7 times 6 is 42. Leave a remainder 12, so 7 does not work. 8, again, we get to use our trick. 8 is twice 4, so can I divide? Certainly, 54. 9, oh, now watch this. 9 is 3 times 3. Can I divide 144 by 3? Now, I know you can, but I'm going to just show you real quick. 3 times 4 is 12, which leaves 24, 3 times 8. So that's 9 times 48. 10 doesn't divide 10 because this isn't a 0 at the end. 11, I'm sure 11 doesn't work, but again, sometimes you just have to do the long division. So that would be 3 of them. 33 leaves a 10 and a 2, 102. And 11 doesn't divide 102, so it's not 11. 12, well, we have a shortcut here. 6 times 2 is 12, and 72 divided by 2 is 36. 13 doesn't divide. 14, 15. 14 doesn't divide because 7 didn't divide. If 14 did, then I'd be able to divide by 7, so that didn't work. 15, 16, 17, yikes. Okay, let's come back up here. 16 would have to be 2 times 8 is 16, so can I divide 54 by 2? And I can. I get 26. And then, well, let me double check that. 25, 26, 27. 17, no. 18, 18 is twice 9. And half of 36 then is 18. Oh, and look, I'm back. So I have the same number here that I have here. So these are all of the numbers that divide 432. So nobody wants to do that. I'll admit that wasn't even fun to do on videotape, or audio tape. But if you needed to find all the factors of a number, it's certainly an easier way than just kind of guessing your way through the whole process. So let me list them out here real quick. And I'm going to bet if you did it by guess and check, or just by going through number by number, you would have run out of steam and just decided that you'll miss that problem. I'll just skip that one on the test. All right, so this was all the factors, right? So this was a process of finding all the factors. And of course, when I say find all the factors, I mean all the integer factors. So on a small number, you can do it just in your head. Follow along one number by number until you get to the end. In a semi-small number, you could probably do that in your head. You might miss one along the way, you might not. But for a larger number, having an algorithm works. And the algorithm that I just showed you works great because you find not only all the factors, but you find all the factor pairs, which is kind of nice to have two things finished when you've done one set of work. But there's another way of factoring a number. It's more powerful. Finding all the factors is useful, but sometimes you just want to find the prime factorization, which means you want to find all of the prime numbers that if you multiply them together give you a number. So this is called prime factorization. And in the end, it's going to let you write a number as a product of primes. You've done this 1,000 times, factor tree, factor birthday cake, factor whatever. I want you to use the factor hockey stick only because it gives you all of your factors on the outside. And when you start simplifying and reducing radical numbers, remember the one with the funny symbol from a previous lesson, when you want to reduce those, the hockey stick method is the most useful method for organizing the prime factors. So let's do the same numbers that we've done already. We're going to use to write as a product of primes. So let's start with 12. Hockey stick method just means that on the right hand side, sort of like we did here, you're going to start with the smallest prime that you can and keep working down the left hand side with those small primes. So the smallest prime number that divides 12, not 1, because if you choose 1, then you're just going to keep repeating 12, right? That's crazy. Nobody wants to do that. So the smallest number, not 12, not 1 that divides 12 is 2. 2 times 6 is one of the factor pairs of 12. But we don't want factor pairs now. We want to find all the prime numbers that multiply to give you 12. So I'm going to take the smallest prime again, and 2 is the smallest number that divides 6, and that leaves 3. And so what I have is, this is why it's called hockey stick. It looks kind of like a hockey stick. What I have is 2, 2, 3, but these are factors of 12. They're the prime factors. If I take 2 times 2 times 3 and I multiply these together, I get 12. So this is called the prime factorization, or the PoP of 12. And this is a super important thing. So let's look at 24 now. Smallest prime, not 1, that divides 24 is 2, leaving 12, which divides by 2, leaving 6, which divides by 2, leaving 3. Now notice how I said that as I was going. Another reason for the hockey stick method is it teaches your brain how to do this without having to draw out the hockey stick. And pretty soon you'll be able to do this in your mind, in your head, without having to draw out the hockey stick. So again, here we are with the hockey stick. So 24 is 2 times 2 times 2 times 3. So that's the prime factorization, or the PoP of 24. Let's do, what was the other number we had? That ugly one? 432. Should we do that one? Yeah, what the heck. Let's go ahead and do it. 432 divides by 2. We know it does because it's an even number. And what did that give us? When we divided it by 2, we ended up with 216. Which divides by 2, leaving 108, which divides by 2, leaving 54, which divides by 2, leaving 25, 27, which divides not by 2, but the next smallest prime is 3, leaving 9, which divides by 3, leaving 3, and last 3 is a prime. So now my hockey stick is right here. You don't have to draw the hockey stick, by the way. And so if I wrote the prime factorization of 432, that would be 2 times 2 times 2, 1, 2, 3, 4 2's, times 1, 2, 3 3's. All right, so this is called the prime factorization. In fact, this is the whole reason algebra exists. The whole reason algebra exists is because for any given number, the factors that make it up are unique. You can never combine 2 2's and a 3 by multiplication and get any number other than 12. If you could, we'd all go home and we'd be done. There'd be no more math. It would all be proven incorrect. Same thing here. 24 is always going to be 3 2's and a 3. They might be written in a different order, 2 times 3, and then the 2 2's afterward, but that part doesn't matter because when you multiply across, you're going to get the same number. Same thing with 432. But notice as I've gotten up into this giant 432 number, writing out the primes, even when you write out the primes, it turns out to be very tedious. So we're going to write this in exponential form. We're going to write 2, and there are 4 of these. And then 3, there are 3 of them. So this says to multiply 2 by itself 4 times. 2 times 2 times 2 times 2 times multiply 3 by itself 3 times. 3 times 3 times 3. Up here for 24, the prime factorization is 2 cubed times 3. And for 12, the PoP, the prime factorization, is 2 squared times 3. So the takeaway here is that you should be able to take any number and write it as a product of primes or a product of prime numbers in extended form or expanded form, which is all written out in the long way, or in exponential form. Okay, you should be able to write all the all the factors of a number, and you should be able to write all the factor pairs of a number.